Welcome to Numerical Methods for Scientists and Engineers. Direct solution of systems of linear equations. Gauss elimination with partial pivoting. A typical linear system of equations with n equations and n unknowns has the following form. Linear systems of equations have a wide range of applications in various fields in science and engineering. The numerical solutions of ordinary and partial differential equations lead to systems of linear equations. Direct solution methods for solving linear systems of equations involve finding an exact solution using a finite number of operations without the need for iteration. Direct solution methods such as Gauss elimination or Gauss-Jordan, covered in the previous video, are ideal for small to medium-sized systems that are well-conditioned and require exact solutions. This lecture focuses on the direct solution method, Gauss elimination with partial pivoting. Every linear system of equations can be expressed in matrix equation form as shown, which is required in the partial pivoting version as well. A is the coefficient matrix, B is the right-hand side vector, and X is the vector of unknowns. The system is set up in an augmented matrix form as illustrated. The augmented matrix, which is an n by n plus 1 rectangular matrix, combines the coefficient matrix and the right-hand side vector of the matrix equation into a single matrix. This is a compact way of representing a system of linear equations. The naive Gaussian elimination is used for solving a system of linear equations by transforming the system's augmented matrix into an upper triangular form, or row echelon form, through a sequence of row operations and then performing back substitution to find the solution. The naive Gauss elimination does not employ pivoting, which would be perfectly fine when solving most linear systems. However, if any one of the pivots turns out to be zero during the elimination process, a division by zero is encountered. In this case, the naive method will fail even if the coefficient matrix is non-singular or the linear system has a unique solution. In this video, the Gauss elimination method that implements partial pivoting technique is described. Consider, for instance, the following system of linear equations and corresponding augmented matrix. The determinant of the coefficient matrix is -10. That is, it is not singular, and the system has a unique solution. However, we cannot start the forward elimination procedure because the scaling or normalization factor becomes 1 over 0 at the first pass. Nonetheless, this problem can be averted by interchanging row 1 with either row 2 or row 3, that is, any row that does not have 0 in its first column. On the other hand, at first glance, the pivots may not be 0, but it is possible to get 0 or very small values in the pivots during the forward elimination procedure. Therefore, it is smart to check the pivot before each elimination process. In this regard, partial pivoting ensures that the pivot element is the largest element in the current column. Partial pivoting eliminates the possibility of divisions by 0. It also minimizes round-off errors by using the largest elements as pivots, which enhances the stability, accuracy, and reliability of numerical solutions. And in some cases, it does offer a remedy for solving ill-conditioned linear systems. While partial pivoting provides the benefits mentioned, there are also some potential drawbacks or limitations associated with this method. Pivoting can lead to an increase in CPU time due to searching for the largest element in a column. The symmetry or regularity properties of the original matrix may be lost. It is computationally expensive for very large linear systems. The pivoting algorithm starts with column 1. The element with the largest absolute value among the elements in the first column is searched starting from the second row to the last row. If A11 is already the element with the largest magnitude, We can go ahead and start zeroing out the elements below the pivot as in the usual Gauss elimination algorithm. But suppose the element with largest in magnitude is in the kth row, that is, AK1 is largest in absolute value. The first and kth rows are interchanged. This places the largest element in the first row pivot position. Once the pivot is in place, we can perform Gauss elimination as usual by using the pivot to eliminate the elements below it, i.e., from rows 2 through in column 1. This process, as we see, eliminates the unknown x1 from all rows below it. Moving to the second column, we search for the largest absolute value in this column from the third row to the last. If A22 is already the element with the largest magnitude, we will carry out the elimination of the elements below the pivot from rows 3 through in, as in usual the Gauss elimination algorithm. However, if the element with the largest magnitude is in row M, that is, AM2 is largest in absolute value, row 2 and row M are interchanged. This operation places the largest element in the second row pivot position. Then, the Gauss elimination procedure can be implemented as usual by using the pivot to eliminate the elements below it in column 2. We continue this process for all columns from row 2 to row n-1. The procedure of checking whether AJJ is the largest in absolute value is carried out for every column. If the current pivot is not the largest in magnitude, it is swapped with the row having the largest absolute value. This process ensures the pivot is not zero and minimizes numerical instabilities. Note that the elements below the diagonals have been cleared to 0 before column J. Here, when swapping the rows, we are essentially storing the value of AJK, or BJ, in a temporary placeholder, then copying the value of a POSK, or BPOS, into AJK, or BJ, and finally copying the stored value from the temporary placeholder into a POSK, or BPOS. The use of a temporary variable allows us to hold one of the values during the swapping process. By the end of this process, the augmented matrix will be an upper triangular form, with all the elements below the diagonal being 0. The solution is obtained by employing the usual back substitution algorithm. Now let us consider a system of 4 equations and 4 unknowns. This system can be expressed in matrix form as the augmented matrix is set up as follows, with the matrix A on the left and vector B on the right side. The augmented matrix is transformed to UX equals B prime, where U is an upper triangular matrix. Now let us consider a numerical example involving a 4 by 4 system, given in the matrix form as follows. The 4 by 5 augmented matrix is set up as follows. The goal of the first pass is to ensure that the pivot in the first column is largest in magnitude, and then eliminate all the elements below the pivot. We note that the one in the first row in the first column is not the largest element in magnitude in this column. The largest element in magnitude is 3 in row 2, so we should interchange row 2 and row 1. Next, to eliminate the one in the second row, we add 1 over 3 times row 1 to row 2. And row 2 is replaced by the resulting row. Next, we add 2 over 3 times row 1 to row 3 to eliminate the -2 in the third row. Row 3 is replaced by the resulting row. Then, we add minus 2 over 3 times row 1 to row 4 to eliminate the 2 in the fourth row. Row 4 is replaced by the resulting row. This also marks the end of the first pass. The goal of the second pass is to ensure the pivot in row 2 is the largest in magnitude, and use the pivot to eliminate all the elements below it. Again, we note that the second row second column element, which is minus 1 over 3, is not the largest of the second column in magnitude. The largest element, which is 17 over 3, is in the third row. Thus, we interchange row 2 and row 3. To eliminate minus 1 over 3 in the third row, we add 1 over 17 times row 2 to row 3. And we replace row 3 with the new row. To eliminate 1 over 3 in the fourth row, we add minus 1 over 17 times row 2 to row 4. The new row replaces row 4. This operation also marks the end of the second pass. The goal of the third pass is to ensure that the pivot in the third column element is the largest in magnitude, and then eliminate all the elements below the pivot. As can be seen, the one in the third row, third column element, is not the largest in magnitude of the elements below the pivot in the third column. The largest element, which is 3, is in the last row. Therefore, we should interchange rows 3 and 4. Next, to zero out the element in row 4, we multiply row 3 by minus 1 over 3 and add it to row 4. The resulting row replaces row 4. This also marks the end of the third pass as well as the forward elimination procedure. The result is an upper triangular system of linear equations. To illustrate the back substitution procedure, we cast the system in equation form. The last equation contains only one unknown, x4, whose solution is easily read as 3. This solution is applied the rest of the equations. The third equation now is an equation with x3 as the unknown. Solving this gives 4, which is also substituted into the other equations. We note that the unknown of the second equation is x2, whose solution yields minus 1. Finally, the first equation is solved for x1 that gives 2. With this, the Gauss elimination with partial pivoting procedure ends here. That is all for now. See you next time with another topic. Bye.